basically any observer that exists inside the universe is going to be computationally bounded.
No, any observer like us. I don't know. I can't.
When you say like
imagine
us, what do you mean? What do you mean like us?
Well, humans with finite minds.
You're including the tools of science.
Yeah. I mean, and as we have more precise, and by the way, there are little sort of microscopic violations of the second law of thermodynamics that you can start to have when you have more precise measurements of where precisely molecules are.
Right.
But for a large scale, when you have enough molecules, we don't have, we're not tracing all those molecules, and we just don't have the computational resources to do that. And it wouldn't be, I think to imagine what an observer who is not computationally bounded would be like. It's an interesting thing because, so what does computational boundedness mean? Among other things, it means we conclude that definite things happen. We take all this complexity of the world and we make a decision. We're going to turn left or turn right. Mm-hmm. And that is kind of reducing all this kind of detail into we're observing it. We're sort of crushing it down to this one thing.
Yeah.
And that if we didn't do that, we wouldn't have all this sort of symbolic structure that we build up that lets us think things through with our finite minds. We'd be instead, we'd be sort of one with the universe.
So content to not simplify.
Yes. If we didn't simplify, then we wouldn't be like us. We would be like the universe, like the intrinsic universe, but not having experiences like the experiences we have, where we, for example, conclude that definite things happen. We sort of have this notion of being able to make sort of narrative statements.
Yeah. I wonder if it's just like you imagined as a thought experiment, what it's like to be a computer. I wonder if it's possible to try to begin to imagine what it's like to be an unbounded computational observer.
Well, okay. So here's how that, I think, plays out.
My brain just broke. Yeah.
So I mean, in this, we talk about this Roolead, this space of all possible computations.
Yes.
And this idea of, being at a certain place in the Roolead, which corresponds to sort of a certain way of a certain set of computations that you are representing things in terms of. Okay, so as you expand out in the Roolead, as you kind of encompass more possible views of the universe, as you encompass more possible kinds of computations that you can do, eventually you might say that's a real win. We're colonizing the Roolead. We're building out more paradigms about how to think about things. And eventually you might say, we won all the way. We managed to colonize the whole Roolead. Okay, here's the problem with that. The problem is that the notion of existence, coherent existence, requires some kind of specialization. By the time you are the whole Roolead, by the time you cover the whole Roolead, in no useful sense do you coherently exist. So in other words, in the notion of existence, the notion of what we think of as definite existence requires this kind of specialization, requires this kind of idea that we are not all possible things. We are a particular set of things, and that's kind of how we. That's kind of what makes us have a coherent existence. If we were spread throughout the Roolead, there would be no coherence to the way that we work. We would work in all possible ways, and that wouldn't be kind of a notion of identity. We wouldn't have this notion of kind of coherent identity.
I am geographically located somewhere exactly, precisely in the Roolead. Therefore, I am. The Descartes kind of.
Yeah, right. Well, you're in a certain place in physical space. You're in a certain place in Roolean space. If you are sufficiently spread out, you are no longer coherent, and you no longer have. I mean, in our perception of what it means to exist and to have experience, right, it doesn't happen that way.
So therefore, to exist means to be computationally bounded.
I think so. To exist in the way that we think of ourselves as existing. Yes.
The very act of existence is like operating in this place that's computationally irreducible. So there's this just giant mess of things going on that you can't possibly predict. but nevertheless, because of your limitations, you have an imperative of like, what is it? An imperative or a skill set to simplify, or an ignorance, a sufficient level.
Okay, so the thing which is not obvious is that you are taking a slice of all this complexity, just like we have all of these molecules bouncing around in the room, but all we notice is, the kind of the flow of the air or the pressure of the air. We're just noticing these particular things. And the big interesting thing is that there are rules, there are laws that govern those big things that we observe.
Yeah.
So it's not obvious that that would be the case.
Because it doesn't feel like it's a slice.
Yeah, well,
It's
right.
not a slice.
Well,
it's like an abstraction.
Yes, but I mean the fact that the gas laws work, that we can describe pressure, volume, et cetera, and that we don't have to go down to the level of talking about individual molecules, that is a non-trivial fact. Mm-hmm. And here's the thing that exciting thing as far as I'm concerned. The fact that there are certain aspects of the universe, so, we think space is made ultimately these atoms of space and these hypergraphs and so on, and we think that but we nevertheless perceive the universe at a large scale to be like continuous space and so on. In quantum mechanics, we think that there are these many threads of time, these many threads of history, yet we kind of span. So in quantum mechanics, in our models of physics, there are these, time is not a single thread. Time breaks into many threads. They branch, they merge, but we are part of that branching, merging universe.
Right.
And so our brains are also branching and merging. And so when we perceive the universe, we are branching brains perceiving a branching universe.
Yeah.
And so the fact that the claim that we believe that we are persistent in time, we have this single thread of experience, that's the statement that somehow we manage to aggregate together those separate threads of time that are separated in the fundamental operation of the universe. Mm-hmm. So just as in space, we're averaging over some big region of space and we're looking at the aggregate effects of many atoms of space. So similarly, in what we call branchial space, the space of these quantum branches, we are effectively averaging over many different branches of histories of the universe. And so in thermodynamics, we're averaging over many configurations of, many possible positions of molecules.
Yeah.
So what we see here is, so the question is, when you do that averaging for space, what are the aggregate laws of space? When you do that averaging over branchial space, what are the aggregate laws of branchial space? When you do that averaging over the molecules and so on, what are the aggregate laws you get? And this is the thing that I think is just amazingly neat.
That there are aggregate laws at all.
Yes, but the question is, what are those aggregate laws? Yes. So the answer is, for space, the aggregate laws are Einstein's equations for gravity, for the structure of space-time. For branchial space, the aggregate laws are the laws of quantum mechanics. And for the case of molecules and things, the aggregate laws are basically the second law of thermodynamics. And so that's the things that follow from the second law of thermodynamics. And so what that means is that the three great theories of 20th century physics, which are basically general relativity, the theory of gravity, quantum mechanics, and statistical mechanics, which is what kind of grows out of the second law of thermodynamics, all three of the great theories of 20th century physics are the result of this interplay between computational irreducibility and the computational boundedness of observers. And, for me, this is really neat because it means that all three of these laws are derivable. So we used to think that, for example, Einstein's equations were just sort of a wheel-in feature of our universe, that they could be, the universe might be that way, it might not be that way. Quantum mechanics is just like, well, it just happens to be that way. And the second law, people kind of thought, well, maybe it is derivable. Okay. What turns out to be the case is that all three of the fundamental principles of physics are derivable, but they're not derivable just from mathematics. They require, or just from some kind of logic or computation, they require one more thing. They require that the observer, that the thing that is sampling the way the universe works is an observer who has these characteristics of computational boundedness, of belief, and persistence in time. And so that means that it is the nature of the observer the rough nature of the observer, not the details of, oh, we got two eyes and we observe photons of this frequency and so on, but the kind of the very coarse features of the observer then imply these very precise facts about physics. And I think it's amazing.
So if we just look at the actual experience of the observer, that we experience this reality, it seems real to us. And you're saying because of our bounded nature, it's actually all an illusion. It's a simplification.
Well, yeah, it's a simplification, right? What's
But you don't think
underneath?
a simplification is an illusion?
No, I mean it's well, I don't know. I mean, what's
real?
underneath? Okay, that's an interesting question. What's real? And that relates to the whole question of why does the universe exist? And what is the difference between reality and a mere representation of what's going on?
Yes. We experience the representation.
Yes. But the question of so one question is, why is there a thing which we can experience that way? And the answer is because this Roolead object, which is this entangled limit of all possible computations, there is no choice about it. It has to exist. There has to be such a thing. It is in the same sense that, 2 plus 2, if you define what 2 is and you plot pluses and so on, 2 plus 2 has to equal 4.
Yeah.
Similarly, this Roolead, this limit of all possible computations, just has to be a thing that is, once you have the idea of computation, you inevitably have the Roolead.
Yeah, you're going to have a Roolead, yeah.
Right. And what's important about it, there's just one of it. It's just this unique object. And that unique object necessarily exists. And then the question is, and then we once you know that we are sort of embedded in that and taking samples of it, that it's sort of inevitable that there is this thing that we can perceive that is, our perception of kind of physical reality necessarily is that way, given that we are observers with the characteristics we have. So in other words, the fact that the universe exists it's almost like to think about it almost theologically, so to speak. And I've really, it's funny because a lot of the questions about the existence of the universe and so on, they transcend what kind of the science of the last few hundred years has really been concerned with. The science of the last few hundred years hasn't thought it could talk about questions like that. Yeah. But I think it's kind of, and so a lot of the kind of arguments of, does God exist? Is it obvious that, I think it in some sense, in some representation, it's sort of more obvious that that something sort of bigger than us exists than that we exist. And we are, our existence and as observers, the way we are is sort of a contingent thing about the universe. And it's more inevitable that the whole universe, kind of the whole set of all possibilities exists. But this question about, is it real or is it an illusion? All we know is our experience. And so the fact that, our experience is this absolutely microscopic piece of sample of the Roolead, and we're there's this point about we might sample more and more of the Roolead, we might learn more and more about, we might learn like different areas of physics, like quantum mechanics, for example. The fact that it was discovered, I think, is closely related to the fact that electronic amplifiers were invented that allowed you to take a small effect and amplify it up, which hadn't been possible before. Microscopes had been invented that magnify things and so on, but having a very small effect and being able to magnify it was sort of a new thing that allowed one to see a different sort of aspect of the universe and let one discover this kind of thing. So, we can expect that in the Roolead, there are an infinite collection of new things we can discover. There's in fact, computational irreducibility kind of guarantees that there will be an infinite collection of kind of, pockets of reducibility that can be discovered.